Good evening, GCC. Welcome back. College Algebra, Math 150 something, 150 or 151. We're going to look at matrices now. This chapter has always kind of annoyed me because in chapter 12.2 and 12.3 they talk about using matrices and determinants of matrices and all that other good stuff. And then it's not until 12.4 do they actually teach you what a matrix is and how to use it. It's all kind of crazy backwards. A lot of times in class, I would teach 12.4 first, or teach 12.4 after 12.1, solving systems with graphing and substitution and elimination, and then teach all about matrices, and then 3 and 4. It seems to make more sense that way. But anyway, here we go, learning about matrices. Most of the things about matrices are fairly simple, but multiplying them is kind of confusing at first, can be very difficult. So, as we've seen before, we know that a matrix is a rectangular array of numbers, and I name a matrix with a capital letter if I call this matrix A, and then I have the entries. I can have 4, 0, negative 3, square root of 2, 1/2, and 7. And the matrix is comprised of rows and columns. The dimensions of this matrix, it's the number of rows by the number of columns. So this would be a 2 by 3, and that's how we'll refer to it, as a 2 by 3 matrix. Each one of the numbers inside is an entry and can be designated as the name of the matrix and then the row that it's in, comma, the column that it's in. So the negative 3 is in matrix A, row 1, column 3. That's the entry there. All right, we need to be able to do a couple of different things with matrices, and we've already done a lot. We did row operations, very confusing, very difficult way of solving systems of equations using a matrix operation. And then we talked about finding the determinant and used Kramer's rule of solving systems using matrices. We talked about creating matrices with coefficients and then adding the constants, creating an augmented matrix. But what I'd like to do right now is just look at matrices in general. So I want to talk about a couple of different things we can do with matrices. So first topic is going to be multiply a matrix by a constant. So suppose I'm giving matrix A as the following matrix. 4, 2, 1, 0, negative 3, negative 5. Now notice this matrix, what are the dimensions of this matrix? This matrix is 1, 2, 3 rows by 2 columns. This would be a 3 by 2 matrix. And I want to find 7A. Now 7, when I multiply a matrix times a number, the 7 actually has a special name. It's called a scalar multiplier. And that's just a fancy way of saying a constant times a matrix. So taking a scalar times a matrix really is as easy as just taking the 7 and multiplying it by all the entries. 7 times 4, 28, 7 times 2, 14, 7 times 1, 7, 7 times 0, 0, 7 times negative 3, negative 21, 7 times negative 5, negative 35. So a scalar times a matrix is really just take the number and multiply it by all of the entries. That's all there is to it. I'm not going to do any more examples. I could do a negative number, I could do a fraction, anything you want. All right, next thing I want to talk about is adding and subtracting matrices. Adding and subtracting matrices. Now, there's one very important rule for adding and subtracting matrices. They must have the same dimensions. They must have the exact same dimensions. If they don't have the same dimensions, then you can't add them or subtract them. And then if they have the same dimensions, then we're just going to either add or subtract depending on whatever it is we're trying to do, corresponding entries. All right, let's look at an example of this. I'm going to give you three matrices here. Here's the first one, 4, 0, 7, -2, -5, 1. And then I'm going to give you matrix B, which is going to be 2, 5, 6, -1, -3, 0. And matrix C is going to be 1, -4, 3, 5, 2, and 1. If you need to copy these, we're going to be using these matrices and doing a couple of different things with these matrices, adding and subtracting and using scalar multipliers. So make sure you've got these copied down. On the videos, I don't always pause in class. I would stop and give everybody a chance to copy down and ask questions. But in the videos, you can just kind of hit pause if you need to. So from using these three matrices, we're going to do a couple of different operations here. First, I want to find A plus C, which means I'm going to add the two matrices together. All right, so let's see. Here's matrix A and matrix C. If I add them together, the sum of the two matrices is going to be, and I'm just going to add corresponding parts. Row 1, column 1, row 1, column 1, 4 plus 1 is 5. 0 plus -4 is -4. 7 plus 3 is 10. -2 plus 5 is 3. -5 and 2 is -3. 1 plus 1 is 2. So as far as finding the sum of two matrices, really that's all there is to it. We just add the corresponding entries together. What if I had asked you to find A plus B? So now the two matrices I'm using are matrix A and matrix B. Now notice this one is a 2 by 3, this one is a 3 by 2. They don't have the same dimensions, so it cannot be done. We can't add those two matrices together. If they don't have the exact same dimensions, then you cannot add them together. That's the rule. All right, so let me give you one to try. Still using these same three matrices. Now I want you to find 2C minus 3A. 2C minus 3A. All right, here we go. So let me try to get everything on the screen here. There we go. That'll work. 2C minus 3A. Well, it's a 2 by 3 and a 2 by 3, so I can combine them. Here's my resulting matrix. 2 times C is 2, minus 3 times 4 is 12. 2 minus 12 is -10. 2 minus -4 is -8. -3 times 0 is 0. -8 minus 0 is -8. 2 times 3 is 6. Minus 3 times 7 is 21. 6 minus 21 is -15. 2 times 5 is 10. 3 times -2 is -6. 10 minus -6 is 10 plus 6, 16. 2 times 2 is 4. Minus 3 times 5, -5 is -15. 4 minus -15, 4 plus 15 is 19. And then finally, 2 times 1 is 2. Minus 3 times 1 is 3. 2 minus 3 is -1. So when it comes to adding and subtracting, that's all there is to it. You're just adding and subtracting, multiplying the scalars in, and then combining the corresponding entries. So adding and subtracting isn't so bad. Multiplying. Now here at the start of the class, I told you that multiplying is going to be tough. Multiply matrices. All right, when multiplying matrices, what I want you to think about, the key is, they may or may not have the same dimensions. I don't have that restriction. The rule is that the number of columns in the first matrix must be the same as the number of rows in the second matrix. The number of columns in the first matrix must be the same as the number of rows in the second matrix. And then, if that's true, then that means you can multiply them together. And the hint for multiplying together is this. Think row times column. So that probably doesn't make any sense right now. You know, what on earth am I saying here? What does that mean? Well, as we start getting into an example, this will make sense. And this is the key. This is the rule. The number of columns in the first matrix has to be the same as the number of rows in the second. Otherwise, you can't multiply them. And then this is really kind of the shortcut, the key, the idea, and how we actually multiply matrices together. All right, so let's take a look at a couple of examples here. In the first one, I'm going to have this matrix, 3, -5, 2. That's a matrix. It's got 1 row and 3 columns. This matrix is a 1 by 3. And then I'm going to take this matrix, which is a 2, a -2, a 4, and a 1, and I'm going to multiply them together. Now this matrix is a 3 by 1. These are often called vector matrices, by the way. A vector matrix either has only 1 row or 1 column. Now, could I add these together? Could I add this matrix and that matrix? No, because they don't have the same dimensions. Could I subtract them? Again, no, don't have same dimensions here. But weirdly enough, I can multiply them. Remember the rule? The rule said the number of columns in the first matrix has to be the same as the number of rows in the second matrix. Now, because this is true, I can actually multiply them together. I'm looking for a pen. Because this is true, I can multiply them together. And remember my hint? Think row times column. If I multiply these together, what am I going to get? The first row, first column times first row, first column. The first row times the first column is going to give me the first row, first column entry here. So my matrix is going to be 3 times -2, or the product matrix is going to be, plus -5 times 4, plus 2 times 1. And if I simplify this, let's see, I'm going to get -6 and -20 and 2. My answer is the following matrix. -26 and 2, -24. That's the answer. Now notice that the number of rows and the number of columns were the same. The number of columns in the first matrix was the same as the number of rows in the second matrix. So this is why I'm allowed to multiply, because these are the same. And notice the resulting matrix has these dimensions. The resulting matrix here is a 1 by 1. That's always going to happen. That relationship is always going to happen like that. All right, let's look at another example. And I think, weirdly enough, this is one of those skills where the more difficult the example, the easier it is to kind of understand what's going along. So what we're going to do is we're going to take this matrix, 1, 2, 3, 4, and we're going to multiply it by this matrix, 5, 6, 7, 8. I want to multiply these together. First, let's see, can I multiply these together? The dimensions of this matrix is a 2 by 2. This matrix is also a 2 by 2. Well, since the number of columns in the first matrix is the same as the number of rows in the second matrix, because those are the same, that means I am allowed to multiply them together. What will be the dimensions of my resulting matrix? The resulting matrix will be a 2 by 2. So I'm taking a 2 by 2, multiplying it by 2 by 2, and I'm going to get a 2 by 2. All right, so now let's actually do the work. And notice I use different numbers here, 1, 2, 3, 4, 5, 6, 7, 8, so that you can kind of track them and see what's going on here. Now, as we multiply these out to find the resulting matrix, keep track of the whole idea. Remember what I said, row times column? So the first row times the first column is going to give me the first row, first column entry. In other words, 1 times 5 plus 2 times 7. The first row times the first column gives me the first row, first column entry. The first row times the second column gives me first row, second column entry. So 1 times 6 plus 2 times 8. First row times second column gives me the first row, second column entry. Second row times first column is going to give me second row, first column entry. 3 times 5 plus 4 times 7. And then second row times second column gives me the second row, second column entry. 3 times 6 plus 4 times 8. I know these are kind of close together. Remember, there's no operation here. These are just numbers. There's no operations here. If I simplify this, let's see, what am I going to get here? 5 plus 14 is going to be my first row, first column entry. 6 plus 2 times 8, 16. 15 plus 28. 3 times 6 is 18 plus 32. So my resulting matrix is going to be 19, 22, 28, 38, 43, 30, 40, 50. There's my product matrix. So if I take these two matrices together and look where all the numbers ended up, can you see the 5s and the 7s, the 6s and the 8s? Can you see the 1s and the 2s, the 3s and the 4s? It's all about that pattern there. And there's my resulting matrix. Again, slow it down. Make sure you're taking notes on this. Look at it. It's all about the pattern. Certainly in class, I would be spending a lot more time doing it a lot slower, spending more time with it, but you can always pause the video and go back and watch it again. Let's look at another example, something a little bit stranger here. Suppose I have the matrix 1, 2, 3, 4, and I'm going to multiply it by the matrix let's make that 5, 6, 7, 8, 9, 0. Take a look at these matrices. Can I multiply them together? Is that possible to multiply these matrices together? This matrix is a 2 by 2. This matrix is a 2 by 3. Well, I've got the same number of columns in my first matrix as rows in my second matrix. Since those are the same, yes, I can multiply together. What are going to be the dimensions of the resulting matrix? 2 by 3. So I'm going to take a 2 by 2, and I'm going to multiply it by a 2 by 3, and my answer is going to be a 2 by 3. And remember the key, think row times column. So as I multiply these together, the first row times the first column is going to give me the first row, first column entry there. So as I multiply them together, I'm going to get 1 times 5 plus 2 times 8. The first row times second column is going to give me first row, second column entry. 1 times 6 plus 2 times 9. First row times third column is going to give me first row, third column entry. 1 times 7 plus 2 times 0. There's my first row. Now I'm going to do second row, and the second row times the first column is going to give me second row, first column entry. Oh, I didn't highlight this one down here, did I? First row times first column gave me first row, first column entry. There it is. So now I'm going to do 3 times 5 plus 4 times 8. And there it is. Second row times first column, second row, first column entry. Second row times second column gives me second row, second column entry. 3 times 6 plus 4 times 9. And then second row times third column is going to give me the second row, third column entry here. 3 times 7 plus 4 times 0. All right, now let's simplify all of these out, and let's see what I get. 1 times 5 is 5. 2 times 8 is 16. 16 and 5 is 21. 1 times 6 is 6. 2 times 9 is 18. 18 and 6 is 24. 1 times 7 is 7. 2 times 0 is 0. 7 plus 0 is 7. 3 times 5 is 15. 4 times 8 is 32. 32 and 15 is 32, 42, 47. 3 times 6 is 18. 4 times 9 is 36. 36 and 18, 36, 46, 54. 3 times 7 is 21. 4 times 0 is 0. 21 and 0 is 21. So there it is. Gosh, here it is. An example of multiplying two matrices. Now notice the number of columns in the first matrix, the rows in the second matrix. I can multiply them together. The resulting matrix is 2 by 3. And there it is. Now, take a closer look at these matrices. And I want you to think about the two questions here. First question, could I add or subtract those two together? And of course the answer is no. They don't have the same dimensions. But I can multiply them together. Here comes the second question. What if I switched them? Could I multiply this times that one? 2 by 3 times a 2 by 2? And the answer is no. I cannot multiply this matrix times that matrix, but I can multiply that matrix times this one. So I can multiply them one way, but not the other way. I know, multiplying is very strange rules. I want to look at one more example, which is, again, very strange. I want you to look at this matrix. Given matrix A is 2, 1, 3, 1, negative 1, 0, and matrix B is 1, 0, 2, 1, 3, 2. I want you to find A times B. Multiply the matrices together. All right, so the first thing I'm going to do is like, well, can I actually do that? The dimensions here are 2 by 3. The dimensions here are 3 by 2. So I'm checking. Are the number of columns in this matrix the same as the number of rows in that matrix? And the answer is yes. So I can multiply them together. I can go a step further than this, and I know that the dimensions of the resulting matrix will be 2 by 2. So I'm going to take a 2 by 3, multiply it by a 3 by 2, and I'm going to get a 2 by 2. I couldn't add these or subtract these. At the very end, after we're done with this, I'm going to ask, could I multiply them the other way around, and what would be the dimensions of the resulting matrix? Interesting question, but let's multiply these together first. So again, as I multiply them, first row times first column is going to give me the first row, first column entry in my product matrix. So 2 times 1 plus 1 times 2 plus 3 times 3. First row times first column gives me first row, first column entry. Remember what I said, think row times column. First row times second column, 2 times 0 plus 1 times 1 plus 3 times 2. So first row times first column gives me first row, first column entry. First row times second column gives me first row, second column entry. Let's keep going. Second row times first column, second row, first column entry. 1 times 1 plus negative 1 times 2 plus 0 times 3. Second row times second column, second row, second column entry. 1 times 0 plus negative 1 times 1 plus 0 times 2. Let's simplify this. I get 2 plus 2 plus 9. 2 and 2 is 4, and 9 I get 13. 0 plus 1 plus 6 is 7. 1 minus 2 plus nothing. 1 minus 2, negative 1. 0 minus 1 plus 0, negative 1. All right, so take a closer look at this. Here it is again with all of the patterns there. Could I multiply them the other way around? Could I find B times A, this times this? Well, the number of rows would be 2. The number of columns would be 2. The number of rows would be 2. So yes, my resulting matrix would be a 3 by 3. So here I'm multiplying a 2 by 3 times a 3 by 2, and I'm getting a 2 by 2. If I did it the other way around, a 3 by 2 times a 2 by 3, I'd end up with a 3 by 3. You know, very strange. The rules for multiplying matrices are very strange. Now, dividing matrices. Let's talk about dividing matrices for a moment. Here's the rules for dividing matrices. Well, that's pretty easy. You can't. There's no such thing as division. You cannot divide a matrix. There's no such thing as matrix division. But there's a way around this. It's something we talk about inverses. So, for example, if I had, let's say, now watch this. If I have the following system of equations, 3x minus 2y equals 4, and x plus 5y equals negative 11. I can rewrite this equation in matrix form. Watch this. The coefficients of x are 3 and 1, y are negative 2 and 5. The variables are x and y, and the constants are 4 and negative 11. So I've rewritten the whole equation in matrix form. So if I think row times column, 3x minus 2y is 4, 1x plus 5y is 11. Did you catch that? I translated this system of equations in standard form into matrix form. Row times column. First row times first column is first row, first column entry. So 3x's and negative 2y's is 4. Second row times first column, second row, first column entry, 1x and 5y's is negative 11. So if I take a look at this, and let's just give the matrices names now. Okay? As we look at the matrices, the first matrix is called the coefficient matrix, because it's the coefficient. The second matrix is the variable matrix, and this matrix is the constants. I'm going to give them names. I'm going to call the coefficient matrix A. The variable matrix I'm going to call X, and the constants matrix I'm going to call it B. And here we have a matrix equation. Matrix A times matrix X is matrix B. The coefficients times the variables are the constants. First row, first column, 3 times x and negative 2 times y is 4. So I've just translated this system of equations in standard form into matrix equation, and then the matrix equation I'm just writing using capital letters. Now if I want to solve this for x, I want to get the variables alone by itself. What is x and what is y? Your first thought is, well, just divide both sides by a. But remember, matrices, we can't divide. There's no such thing as division. So how do we solve this matrix equation? Well, if I want to get rid of the a, and I'm not allowed to divide by a, what other way can I get rid of a? I'm going to turn a into 1, just the unit 1. And what I'm going to do is I'm going to multiply both sides by the inverse of matrix A. So the inverse of A times A. And what happens here, and here's where I just want to focus in on the matrix equations, an inverse times a matrix is just 1. In matrix math we call it the identity. And the identity times anything is just the matrix. In effect, these are canceling each other out. So now if you take a closer look at this, you're going to realize that we have a new method for solving systems of equations using inverses of matrices. Okay? So let's take a look at how do we find an inverse, what can we do with it, and how do we solve systems with inverses. And sometimes some matrices might not have an inverse. Remember Kramer's rule? If the determinant of the coefficient matrix was 0, you can't solve it using Kramer's rule. That doesn't mean there's no solutions. It just means you can't solve it. If a matrix doesn't have an inverse, well, that just means we can't solve it using inverses. All right, so I'm going to give us two matrices here, and I'm going to tell you ahead of time that they are inverses of each other. So I'm going to give you matrix A, which is the matrix 3, 1, 2, 1, and matrix A inverse, which is the matrix 1, negative 1, negative 2, 3. And I want you to find A times A inverse. We're going to multiply the matrix times its inverse together and see what happens. All right, here we go. So first row times first column, 3 times 1 plus 1 times negative 2. First row, second column, 3 times negative 1 plus 1 times 3. Second row, first column, 2 times 1 plus 1 times negative 2. Second row, second column, 2 times negative 1 plus 1 times 3. Simplifying, 3 and negative 2 is 1, negative 3 and positive 3 is 0, 2 and negative 2 is 0, negative 2 and 3 is 1. Ladies and gentlemen, this is the identity matrix. This is the matrix we often refer to with a capital letter I, the identity matrix. It's all zeros with 1 down the main diagonal. They basically cross each other out. We've seen this before, way back in 12.2. This was something we were trying to get to with row operations. So we know that 1x and no y's is whatever the number is over here, and no x's and 1y is whatever it is over here. So the identity matrix, this is what we want to know. All right, so finding the identity matrix can be kind of tough. The problems that I've given you, they're all going to give you the identity matrices. You won't have to worry about the identity matrices. It's going to give you the inverse matrices. This is the inverse matrix here. All right, so let's take a look at a sample problem now. Out of the homework, the first section is going to be fairly easy. They're going to be adding matrices, subtracting matrices, multiplying by a scalar, that kind of stuff. The matrices have to have the same dimensions, otherwise you can't do it. The second set in the homework, you're going to be multiplying matrices, and always you want to stop first and check. Make sure the number of columns in the first matrix is the same number as rows in the second matrix. And if it's not the same, then say it's not defined. You can't do it. And then in the next set, we're going to use inverses to solve each of the systems. So let's do one from the second set. In number 30, in problem number 46, it gives me the following problem. 3x minus y equals 8, and negative 2x plus y equals 4. Now, if I look back in problem number 36, so if I call, if I put this in matrix form, in number 36, in problem 36, it gives me the following matrix: 3, negative 1, negative 2, 1, which is the inverse of that matrix right there. So they're inverses of each other. 36 and 46 go together. Just like 35 and 45, you have to do both of those. 37 and 47 go together. 39 and 49, 41 and 51, and 43 and 53. They all go together here. So first thing I'm going to do is I'm going to translate this into matrix form. And I'm going to get the coefficient matrix, 3, negative 1, negative 2, 1, times the variable matrix of x and y equals the constant matrix of 8 and 4. Now what I'm going to do is this is my inverse matrix here. So think about if this is matrix A times x equals B, this is the inverse of A. That's the inverse. The problems are inverses of each other. So I'm going to multiply both sides by inverses. The inverse of A times x equals the inverse of A times B. These are going to cancel each other out. So what I'm really trying to find is this times this. The matrices that I'm interested in are the inverse of matrix A and the constant matrix. I have to multiply those two together. And when I do, I should get my solution. Let's see how this is going to work. So the inverse of A times B. Well, the inverse of A was matrix 3, negative 1, negative 2, 1. Matrix B was the constant matrix of 8 and 4. So inverse of A, there it is. Matrix B, the constant matrix, here it is. Can I multiply these together? Well, let's see. This is a 2 by 2. This is a 2 by 1. And I notice that the number of columns in my first matrix is the same as the number of rows in my second matrix. So yes, I can multiply them together. And when I do, what are the dimensions of the resulting matrix? The resulting matrix will be a 2 by 1, just like this one. There'll be two numbers there. And that's going to be the answer to x, and that's going to be the answer to y. All right, so here we go. We're going to multiply them together. Again, think row times column. First row times first column. I went too far on that. First row times first column gives me first row, first column entry. 3 times 8 plus negative 1 times 4. Negative 2 times 8 plus 1 times 4. And I'm going to get, let's see, 3 times 8 is 24 minus 4, and negative 16 plus 4, 20, negative 12. There's my solution. That's the solution to the original equation. Now, the original system of equations. Let me just pull that up again. Here it was, right? Here was the original system. Let me kind of blank it out so you can only see the original system here. There we go. So this was the original system. So we took the coefficient matrix times the inverse matrix. The coefficient matrix, there it is, times the inverse matrix. The inverse matrix times the constant matrix. The inverse times the constant, there it is. So this was a to the negative 1 times b. We got this, which means the solution to the system of equations is the point 20, negative 12. X is 20, y is negative 12. All right, so matrices, very confusing, very frustrating, very difficult. There's a whole branch of mathematics. There's a whole class you can take. We don't offer GCC. It's a much more advanced class. You really need calculus before you can do matrix mathematics. But there's a whole class you can take just on matrix math and doing just all sorts of different mathematics with matrices. All right, so now I want you to do the homework from 12.4. It starts on page 916. And as I said, it really kind of comes in 3 sets here. I want you to do problems 9, 11, 13, 17, and 19, and 25 actually. 25. All of these problems are adding, subtracting, multiplying matrices, multiplying times scalar, and all that kind of stuff. Where we really get into the systems are the problems 25, 27, and then 31 through 47 odd. And as you're solving these, look back to problems 31. Look back to problems 31 through 47. We want to look back to the previous problems for the inverses. Problems 27 through 34 are the inverses of problems 35 through 44. Okay, so these matrices are the inverses of those matrices. So when you have to solve this using inverses, you look back to the previous problems, and those are where the inverses will be. All right, and as always, as soon as you're done with the assignment, go ahead and email it to me. I'll grade them and get them in the grade book. Good luck. Another difficult, awkward, frustrating lesson. Not so bad. We've still got 2 more sections to go in this chapter. We're going to do, actually we've got 3 more sections. We're going to skip 12.5, and we're going to go to 12.6 and 12.7, and then 12.8. And then we're going to jump to chapter 13, but only do a couple of topics out of chapter 13. So just like chapter 6, this is a very long, lot of stuff going on in here. This matrix stuff is new, very frustrating, very confusing, very difficult. You can also watch videos on Khan Academy and other resources and other places. You can search them. Try to find other resources that might help you. All right, guys, good luck. If you got any questions, shoot me an email. If not, I will talk to you again soon. Bye.